Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a short break from talking about the normal distribution and focus a little bit on the z-score as a measure of relative position. So far, in the past couple videos, we've been focused on using the z-score in conjunction with normally distributed data. As we've sort of seen, this is a very powerful technique since when we have normally distributed data, we have access to that table A, which tells us a tremendous amount of information about the given population based on the z-score. We were able to do things like calculating the percentage of the population that was above a certain value, below a certain value, between two values. We were also able to take based on an individual's percentile rank and actually calculate the value of whatever variable we were studying for that individual. Now, while table A is restricted for use with normally distributed data, so to use that table A, we need to know that the data is normally distributed. The z-score itself is not. Remember, the z-score is just that calculation of taking a data point minus the mean divided by the standard deviation. You can do that for any data set that you have. In fact, the z-score is a great tool for understanding relative position in any data set. Remember that a z-score measures the number of standard deviations above or below the mean a given data point is located. So remember, what the z-score is really doing fundamentally is trying to tell you where a data point is located relative to the mean based on the standard deviation. In other words, we can use the z-score to standardize data relative to the mean based on the standard deviation. And what we mean by standardize is that the z-score gives us a way of sort of comparing values or individuals from different populations against one another on sort of a level playing field. And what levels that playing field? Well, that would be the z-score. So, for this video, we're going to look at a couple examples of using the z-score as this measure of relative position. And then after this video, we'll return back and finish up the normal distribution. So in this, we won't be doing anything with assumptions about data sets being normally distributed. We'll just be focused on using the z-score as a measure of relative position. So let's go ahead and get started with a couple examples here. So for our first example, we're going to suppose that we're studying the points scored per game by 4 basketball players during their career. So we collect the following data about each of the players' career performances. So we have our players, player 1, player 2, player 3, and player 4. Player 1 averaged 13.4 points per game with a standard deviation of 6.2. Player 2 averaged 11.8 points per game with a standard deviation of 2.3. Player 3 averaged 8.6 points per game with a standard deviation of 5.9. And player 4 averaged 23.2 points per game with a standard deviation of 5.6. So we can say right here, this is their career performances, basically how they've performed during their entire career. Now we're going to suppose we further look at a particular playoff game, so just a sort of special game we're interested in, where all 4 of these players played. In this particular game, player 1 scored 15 points, player 2 16, player 3 18, and player 4 21. So we're going to do a couple things with this information. We're going to take a look at sort of understanding sort of what all the information is saying, and then we'll actually get to using the z-score to answer some interesting questions here. So the first thing we're going to do is we're going to order the players from highest to lowest in terms of average points scored per game for their career. So in other words, in part A here, we're going to sort of rank the players from best to worst, at least in terms of the average points they scored per game during their entire career. So this should be pretty easy, right? If we're trying to go from highest to lowest in terms of average points scored per game, well, if we look at the averages, player 4 was far and away the best in terms of average points scored, so we put player 4. Then in terms of second place, it's pretty close, but player 1 had 13.4, so player 1. Then player 2 with 11.8. And then finally, sort of the lowest in terms of average points per game, player 3. Now, of course, that doesn't necessarily mean that they were the best or worst players, right? I mean, a lot more in basketball than just scoring points. But in terms of actually just looking at points scored, we'd say player 4 had the best career average, 23.2, and conversely, player 3 had the worst average of only 8.6. Okay, let's go ahead and answer another question sort of related to their career. We're going to order the players from most to least consistent in terms of points scored per game for their career. So we're looking at most to least consistent. And remember, we discussed that for consistency, you can measure that with the standard deviation. Remember, a high standard deviation means lots of variability, which means being inconsistent. A low standard deviation means very little variability, which means being very consistent. So if we look at this, the player with the lowest standard deviation, so who was most consistent, was player 2 with only 2.3. So we'd put player 2 first. Then, it's close, but player 4 was actually the next most consistent, so player 4. Then the next lowest would be player 3 with 5.9 as their standard deviation. And then player 1 with 6.2. So there we go. So most consistent was player 2, right? Doesn't mean that they necessarily scored the most points. In fact, it basically means that they were usually very close to their average of 11.8 because their standard deviation was quite small. And then player 4, player 3, and player 1 were all less consistent, with player 1 being the most sort of inconsistent, meaning that they were sometimes probably very sort of less than their average, and sometimes they might have been a lot higher than their average. Again, nothing sort of good or bad intrinsically about being inconsistent, but it is sort of an important piece of information we can get from their career stats here. Okay, let's look at part C here, which says that we want to order the players from highest to lowest in terms of points scored, but not in their career in the playoff game that we are studying, so in this particular game. So this should be very straightforward. So we just want to order them from highest to lowest in terms of points scored in this game. Well, we can see that player 1 had 15, player 2 16, player 3 18, and player 4 21. So the highest would be player 4, and then player 3, then player 2, and then player 1, right? With player 1 and player 2 being very close, but player 4 definitely being the top with 21 there. Okay, so in terms of all these things, no z-score was necessary because notice we weren't trying to do anything relative to their performances. But part D will allow us to actually start to use that z-score and answer a much more interesting question. What we're going to do is we're going to order the players from best to worst performance in terms of points scored in that playoff game, but relative to their career performance. Now, why is this sort of an interesting question? Well, if you think about it, if we just, without even calculating anything, you can see why this is sort of a unique question. Take player 4. Player 4 in that playoff game scored 21 points. He scored the most out of the entire group. But if you think about it, compared to their career average, it wasn't a very good performance. Their career average was 23.2. So scoring 21 was not a very good performance for this particular player. On the other hand, if you take somebody like player 3, they scored 18. Okay, 18 is definitely less than 21, but keep in mind they're a career average of 8.6, and 18 is way above that. So they played in that single game much better relative to their general performance. So this is what we're going to try to understand in part D. So the key thing here is if you see something that mentions relative, that means you want to try to use the z-score. So what we're going to do is we're going to calculate a z-score for each of the players' performances relative to their career statistics. So let's go ahead and do that. So for part D, let's go ahead and calculate a z-score for player 1. Remember, player 1 scored 15 points, and their average and standard deviation were 13.4 and 6.2. So we would take their actual data point of 15 minus their career average of 13.4, and we would divide by their standard deviation, which was 6.2. If we calculate that, we can see that they were 1.6 points above average, 15 minus 13.4, and then dividing that by 6.2, we can see that that was approximately 0.26. So they were a little over a quarter of the standard deviation above average. Okay, well, let's go ahead. We'll sort of just put a line here so that we can sort of separate it. Z2, so this will be the z-score for player 2. Remember, player 2 scored 16 points, and that's going to be compared against their average of 11.8 and 2.3. So that's 16 minus 11.8 divided by 2.3. And if we look at that, 16 minus 11.8 means that they were 4.2 points above their average, divided by 2.3. But notice that this comes out as about 1.83. So notice that they were close to 2 standard deviations above average. Why is that? Because remember, that particular player, player 2, has very little deviation. So to be 4.2 points above their average is quite significant, given that they generally didn't have a lot of variation in their career. All right, for Z3, which would be for player 3. Remember, player 3 had an average of 8.6 and a standard deviation of 5.9. So we'll take the 18 there. 18 minus that, what was it, 8.6, and divided by 5.9. So 18 minus 8.6, they were 9.4 points above their average, divided by 5.9. And we see that that comes out as about 1.59. So they were a little over 1.5 standard deviations above their average. Finally, for player 4, and then we'll actually put all this together. For player 4, they scored 21 points versus an average of 23.2. So 21 minus 23.2 divided by their career standard deviation, which was 5.6. So we'll have 5.6 in the denominator. Notice that they'll have a negative up top, negative 2.2, because they were 2.2 points below their career average. And if we do that division, right, we would say negative 0.39. So notice that they have a negative z-score, even though they scored the most raw points. Compared to their average performance, they were actually below average. All right, now let's go ahead. We can draw ourselves a little sort of number line to help understand this. There's 0, which would be an average performance, right? If you, let's center that a little bit. Don't know why it's off center there. There's 0, which would be an average performance. If you have a z-score of 0, that means you performed as your average. Okay? So if we sort of label on here, maybe we can put 1 and 2, negative 1, negative 2. So Z1 would be located at 0.26, which would be right about there. So there's player 1. Player 2 would be 1.83, which would be located over here. Player 3 was 1.59, which would be probably somewhere right about there. And then, of course, player 4 was negative 0.39, so they would be located somewhere over there. Now, the only thing we need to make sure of is, remember, we're trying to do best to worst. So in terms of scoring points, we probably all want to score more points rather than less. So this would be sort of worse, and this would be better, right? The further you are above the average, the better you did. Now, again, that's not always the case. Whenever you see better or worse, you have to be very careful, because sometimes high scores are good. Scoring high amounts of points are good in basketball, on tests, etc. But if you were thinking about like the time it takes to finish a race or a puzzle, you'd probably want low scores, because that meant you did it more quickly. So whenever you see worse or better, you have to be very careful. In this case, right, better is definitely meaning above average. So we can see that the ordering we should give them is that player 2 actually did the best relative to their career performance, then player 3, then player 1, and then player 4 did the worst. So this is very interesting, because notice that player 4 had the most points in that game. But in terms of their comparison to their career, they should be the most disappointed. They actually did the worst compared to what they typically did, right? They were actually below their average. Notice that player 2 was actually at the third lowest in terms of the actual points, but they should be the happiest because they were so far beyond their average based on the amount of deviation. Last thing I want to just make a comment on here is notice that it really matters that we're not just measuring the difference between how they performed and their average. We're measuring the difference between how they performed and their average based on the standard deviation. That's really important when you look at player 2 and player 3. Notice player 2 was only 4.2 points above their average, but for player 3 they were 9.4. So in terms of just raw difference, player 3 was further above their average. But we base it on the amount of deviation. Player 3 was a sort of notoriously inconsistent player, standard deviation 5.9. So being 9.4 above when you have a standard deviation of 5.9 isn't as significant as being 4.2 points above average when you only have a standard deviation of 2.3. right? We're basically saying player 2 really rarely drifted beyond their average, so being 4.2 points above their average was a big deal. All right, so this gave us our first sort of example of using the z-score to understand relative performance, right? It's not fair to just compare each player's performance in the game against one another because they all sort of perform differently via their careers. It doesn't change the actual points that scored in the game or, the conclusion of the game or anything, but if you're thinking about how they performed relative to how they typically perform, we get some very interesting information there. All right, let's try this again in sort of another situation here. All right, for this example, we're going to suppose that we have 4 friends, again, carefully named alphabetically. We have Aaron, who's a male, age 28, Brenda, who's female, age 26, Carl, who's male, age 57, and Danny, who's female, age 55. All these 4 friends run in a 5K. It takes Aaron 28 minutes to finish the 5K, Brenda 29 minutes, Carl 43 minutes, and Danny 35 minutes. After the race, the friends look up the overall statistics for everyone who ran in the 5K and find the following information, and all these values are in minutes. So a lot of times, if you've ever looked at or competed in like a race or a 5K or a marathon or something, what you'll see is that they'll break down the information by age bracket and also gender. So we get these pieces of information. Males who were 25 to 29 years old averaged a completion time of 31 minutes with a standard deviation of 14. Females who were 25 to 29 took an average of 36 minutes with a standard deviation of 13. Males who were 50 to 59 took 37 minutes on average with a standard deviation of 24. And females who were 55 to 59 took on average 45 minutes with a standard deviation of 25. All right, so we've got some things that we'd like to do. The first thing we want to do is we want to order the friends from best to worst in terms of actual finishing time for this 5K. Do we need to use the z-score here? Well, no, it says actual finishing time. So we want to just look at how they finished. So let's think about who did the best. So if you think about a race, right, the smaller the value, the better you did. If you were actually like the 5th friend of this group, and hopefully your name starts with E, because otherwise I guess you wouldn't fit in with their ABCD format here. If you were their 5th friend and you were watching them, who would actually cross the finish line first? Well, it would only take Aaron 28 minutes, so he would come in first. Then, in terms of the next time, it would be Brenda, who would be just 1 minute behind him. So a minute later, she would cross the finish line. Then, 6 minutes after Brenda finished, Danny would cross the line because she took 35 minutes. And then, after 8 minutes, right, because she took 35 minutes, Carl would cross the line at 43 minutes in total. So in terms of their performance from best to worst, right, Aaron crossed the finish line first, then Brenda, then Danny, then Carl. Okay, but is it really fair to compare them just in terms of the time that they finished? I mean, is it really fair to take people who are 25 and 29 years old and compare them to 50 to 55-year-olds, or 55 to 59-year-olds? Well, notice that in part B, what we want to do is we want to order the friends again from best to worst, but in terms of their finishing time relative to their gender age bracket. So, since we're doing relative here, again, that indicates that we want to use the z-score. So we're not going to just look at their raw finishing times. We're going to look at how they did compared to people that were of the similar age and of the same gender. So let's go ahead and do that. For the z-score for Aaron, what we would have to do is we'd have to take his time, which was 28 minutes. We'd compare that against the average for people like him, 31 minutes, and divide by the standard deviation, 14. Notice we get -3 over 14, and then if we do that division, -3 divided by 14 gives us a z-score of about -0.21. All right, notice that this is a negative z-score. Does this mean that he did badly? Well, not in this case, right? Because actually being lower than average is good here, because running a race, you want to be below the average. So this means he was just slightly below the average, but he should certainly be happy compared to the fact that typically people like him took 31 minutes. He only took 28. All right, let's see about Brenda. So for Brenda, her finishing time was 29 minutes. So we want to compare that 29 against people like her who had an average of 36 divided by a standard deviation of 13. that should be minus 7 divided by 13. And if we do that, minus 7 divided by 13, we can see that hers should come out as about negative 0.54. So she was a little beyond half a standard deviation below average for her gender and age bracket. For Carl, we can go ahead and look at that. Remember, he actually took 43 minutes versus an average of 37. So we'd have 43 minus 37 divided by the standard deviation, which was 24. That would be 6 over 24. And if we do that division, 6 divided by 24, we should see that that was 0.25. Now, of course, we can know, even without any sort of fancy statistics like we're doing with these z-scores, that Carl should be the sort of least happy or maybe the most disappointed in terms of this, because if you think about it, all the other friends, Aaron, 28 versus an average of 31, okay, he's below average, meaning he's did better than the average. Brenda, 29 versus 36, definitely better than average. Danny, 35 versus 45, definitely better than on average. But Carl took 43 versus an average of 37. He's the only one who is slower than people like him. So even without the z-score, we know he didn't do so well, and we can see that by him having the first positive z-score in this situation. For Danny, let's go ahead and do that. Remember, her time was actually 35 minutes. So we take that 35 minus the 45 and divide by the standard deviation of 25, because we're using females 55 to 59. So that looks like we should get negative 10 divided by 25. So remember, this numerator is telling us in raw minutes how much faster she was than on average. She was 10 minutes below the average. But now we need to divide that by the standard deviation, and we can see that that comes in as negative 0.4. So let's do our same thing. Let's go ahead and put a number line here. So we'll put, there's the 0, and remember that means that's an average performance. There's positive 1, there's negative 1. Let's locate each of these on here. So Aaron, negative 0.21, that would be somewhere like there. So there's Aaron. For Brenda, negative 0.54, so that would be somewhere maybe there. For Carl, 0.25, that would put him on the other side over there. And for Danny, negative 0.4, that would put her somewhere right about there. Okay, now, which side is sort of better, which side is worse? Well, again, for a race, you want as low of a time as possible. So this is better over here, the further below average you are, and this is sort of bad on this side. So if we see that, in terms of the order of how they finished relative to their gender and age bracket, we would order them as Brenda did the best, then Danny, then Aaron, then Carl. So notice, interestingly enough, the person who came across the finish line first, Aaron, actually was the third best in terms of his performance relative to gender and age bracket. Brenda, on the other hand, she came across the finish line second, but she should be actually the happiest relative to her gender and age bracket. In other words, if you were saying who's the best runner of them, relative to who they are and their age and everything like that, you'd probably say Brenda is, because she did the best relative to people like her. Okay, let's go ahead and take a look at one more piece of this. Let's go ahead and suppose that Aaron's performance relative to his gender age bracket stays constant over time. How long should it take him to finish the 5K when he is between 55 and 59 years old? So let's think about what we can do with that. So we know, if we think back, that the z-score for Aaron, once we calculated that, was negative 0.21. And we're going to assume that this is somehow fundamental to him. In other words, this is basically a measure of how good of a runner he is. He's basically a runner who is about 0.2 standard deviations below average in terms of finishing time, so that's a good thing, of course. So what we're going to then do is, of course, when he ran, he was 25 to 29. But we're sort of assuming that this stays constant with him as he gets older. So remember, for males 55 to 59, right, we saw that their average was 37 minutes. And their standard deviation, we saw, was 24 minutes. So let's make a prediction of how Aaron will perform once he's 50 to 59. So how do we do that? Well, we can set up our z-score formula, And if we think about it, we're going to assume that he continues to perform at the same z-score, so we can plug that in, negative 0.21. We're trying to figure out what his actual time would be, but notice we'll use the average and standard deviation for the future bracket that he'll be in. So minus 37 and divide by 24. So now we can solve this. We can multiply the 24 over, so negative 0.21 times 24, and we should get negative 5.04 equals x minus 37. We can add the 37 over to the other side and get 31.96 equals x. So when n is 55 to 59, we expect it will take him 31.96 minutes. So what are we doing with this? Well, this is just showing you guys another possibility with z-scores, which is basically that they can be used to make predictions if people change from one population to another. So in this case, we're saying that if his running ability stays constant and he keeps the same relative position in the future, then his performance when he's older, yes, it'll take him 31.96 minutes, which is longer than it currently does, but it'll mean he'll continue to perform the same way relative to the group. Now, of course, is it a guarantee that his performance stays the same? Well, no. I mean, maybe he gets more serious as a runner as he gets older, and he actually does better and better relative to his age group, or maybe he stops running and he gets worse and worse. So, I mean, we are making a big assumption here that he continues to perform at the same relative position. But this can be useful. This is sometimes used in like sports, for example, to sort of diagnose how teams would have performed in different eras of sports. This can also be used, like we said, if we only got information about, say, an athlete when they were older, we could use something like this to sort of make a prediction of how they would have performed when they were younger, or vice versa. There are some uses for assuming this sort of constant relative position and making predictions like this. Okay, so this gave us sort of two examples of using the z-score as a measure of relative position. One thing I want to just call your attention to before we call it good here is that notice that in neither of these questions did we say anything about the shape of the distribution. In this one here, we had these players with their career average and standard deviation, so we knew their average and standard deviation, but we never said anything like their scoring was normally distributed. It's not an important assumption because notice at no point did we use Table A. We were just interested in looking at these z-scores. Could we have used Table A? No, because we don't know that it's normally distributed. If it's not necessarily normally distributed, we can't make use of that normal table, Table A. But we can certainly still use the z-scores. Same thing here. There was no mention that the time it takes to finish a race is normally distributed. It probably isn't normally distributed, actually. Usually finishing times for races are right skewed because there'll be a few people, especially in like a 5K that's casual, that take much, much longer than everybody else. So there's no statement that it's normally distributed. It probably isn't normally distributed. But again, we didn't need to use Table A. We just wanted the z-scores, and you can do that for any distribution. All right, this pretty much wraps up our quick discussion, or a little bit of a sort of a tangential discussion about relative position. In our next video, we'll return to working with normally distributed data, and we'll see how the predictions we make from something like Table A and the empirical rule actually apply to real data and samples.